Now, chapter 10 is about the proof by mathematical induction. So we are going to solve different types of problems with using these methods. So these methods later on we can use when we study complex numbers in more details or differentiation. Also, we will use this method to prove. Then also we can use in trigonometry in the sequences, so it can be used in different areas. So it's just one type of the method. Okay, so what does it say? It's like a stair. Okay, there will be given a statement. What's the statement is? For example, 1 plus 2 plus 3 plus 4 plus till some number n, right? We know for the arithmetic sequence it has a formula if you want to find the sum, or shortly, if you remember the Gauss rule, the Gauss formula, the formula was like this. So there is a statement and I want to prove it. For example, you can easily prove again by sequence, but for example, if it's given in this way or different formula, and they tell you that this is the formula, you want to check it whether this formula correct or not. So what you are going to do, you are going to prove by mathematical induction. Always, first step, you need to check the first step. First thing to do, check the basic step. In some books, they call it basic step, or they call the first step. You have to check it. And the second, what you need to do, you will assume that this formula works for some step n equals to k, for k to be an integer. Okay, and then by using this assumption, you are going to prove that it is correct for the next step after the k step. Okay, so it's like the stairs. For example, you have a stair, it goes to some number n. Okay, and you need to prove it, whether I can walk on this stair or not. First of all, you always need to check, it's just making similarity here. You have to always check whether there is a first step, whether your formula is correct for the first step. Then you will assume that it's correct. Okay, let's say it's correct for the k step. If it's correct for the k step, can I walk from this step to the k plus 1 step? If you can, this formula shows it, then you say that you can prove it. You prove that this statement is correct. Okay, so this one is assumption. By using the assumption, we are going to prove k plus 1 step. Okay, let me show in practice, and let's prove it by mathematical induction, this formula. And also in your book, example 6 and 7, check them. We will go in a different way from your book. In your book, they are showing very good examples, but they start with the divisibility, but we'll go from the formulas, then we'll go to the divisibility, then we'll go to the sequence and trigonometry. Okay, these problems, check it. For example, let's go with the example, with the basic one. Our statement is addition of n numbers is given by this formula. Okay, for this type of problems, how we are going to solve, and the solution, how we are going to do it. In your book, they define this one as a statement. For example, the statement can be defined like this: p sub n or p bracket n. Just shortly, the statement is this one. Just to use it later on in your work, instead of writing all these formula, all these number, you can just call p n. Okay, your statement is. Now, this one, what does it say of first thing? Check basic step, first step. So let's check for the basic step, p1 at the first step. Okay, for this type of questions, the left hand side you will have only 1, right? Because it's the first step, it's a 1. How about the right hand side? Right hand side will be, instead of n, we should put 1 plus 1 divided by 2. As you can see, it will be 1. So as you can see, if you have both of them, left hand side, right hand side, equal, then you say that the first step is correct, is true. Okay, it holds. The first step is correct. So we're done with the first step. Second step, I will assume it is correct for the k step. Which step? I don't know. K step, it's correct. So it means that 1 plus 2 plus 3 plus 4 plus some k equals to k plus 1 divided by 2. I make this assumption. And now in my third part, I need to prove that my aim is, I need to prove that the next step, I'm going to find the result, what's going to be if I include k plus 1 into my statement. If I put the next step, my question is whether I will get this result. If I get this result, then your statement is correct. You prove the statement. So I'm going to come to this conclusion. From where? From this one. Let's try to solve it now. It's my aim. I want to come to this conclusion. I just wrote it for you to see. It's my aim. I want to comment. I cannot write it directly because it doesn't make any sense. Now, let's solve the left-hand side. I need to solve the left-hand side. If I solve the left-hand side and I get this right-hand side, then it means that this one is correct for the k plus 1 step also. So the left-hand side, look at here. This one, I need to use my assumption. That's why we assume it. Instead of 1 plus 2 plus 3 plus k, I can write k plus 1 divided by 2 plus k plus 1. So pay attention here. This one is this form, and this one is from our assumption. Okay, I do assume it. Now, what's equal to? Let me simplify. Let me give common denominator. So what will be if I open the brackets, k squared plus k plus 2k plus 2 divided by 2. Now, my aim is this one. I want to get this expression. If I get it, then it's correct. How I can get it? Let's look how I can simplify it. Can we rewrite it as, okay, this one we can simplify it. How we can simplify it? So it will be k squared plus 3k plus 2, right? If you factorize it, what's it? K plus 1, k plus 2 divided by 2. As you can see, it's actually same. You came to your aim. If you do came to your aim, then you are done with the proof. So at the end, you just write like in your book if you want, or you can just long sentences in your book. They go with a short one. You can write since the first step is true and the k plus 1 step is also true whenever pk is true, then our statement is true. Okay, let me write it here. Then our statement Pn is true for all. Okay, I should include the integers here, and for all integers. Is true for all. Okay, whatever is true for n of the integers. I also want a problem from your book, just to give the idea what to do, how we do follow the mathematical induction. So this one is called proof by mathematical induction. Sorry for the now. Here, let me do part A. Part B is just the solving by using the formula. Okay, the statement is given. Let's make a solution. Pn, our statement is 1 times 2 times 3 plus 1 divided by 2 times 3 times 4 plus, okay, 1 divided by n plus 1, n plus 2 equals to n plus 3 divided by 4, n plus 1. I just rewriting it again. So this one, I'm just showing you how you should also write in your papers, in your solutions. Now, this one, our statement, first thing to do, our first step. Here, pay attention, it gives you what kind of n's you should choose. If it's natural number, you should not from the 1, you should start from the 0, or whatever they tell you. As it says a positive, we will start from the 1, right? Positive numbers, and it starts from the 1, we don't have 0. So what will be, because if you put 0, it makes nonsense here. So for the first step, our first thing to do, I just input, here is my 1, or here is my first element. It will be 1 times 2 times 3. It's a left-hand side. Sorry, I forgot the left-hand side equals this. So what's it? 1 by 6. How about the right-hand side? Right-hand side, according to this formula, 1 plus 3 divided by 4, 1 plus 1, 1 plus 2. So it will be 4 divided by 4 times 6. These two will cancel, so we have 1 by 6. So here, as you can see, the left hand side and right hand side are equal. So your first step, your basic step, is true. Now, it's our first thing to do. Second, we assume this one is correct for k step. So it means that this one is correct for k step. And you have to use this assumption. This part is very important. If you are not using your assumption, then you are doing something wrong. So 1, k plus 1, k plus 2, you assume it's correct. K plus 3, 4, k plus 1, I chose very long question. K plus 2, so it's how you do. You make assumption, then you need to show, you are going to show what happens to the p sub k plus 1. So what is it actually? 1 times 2 plus till k plus 1, k plus 2. Then I include the k step here. After this k, I include the cases. So it will be 1, k plus 1, k plus 2. I'm instead of k now putting k plus 1. Instead of n here, I'm putting k plus 1, k plus 3. Now here I do not put the equality in the first question. I just wanted to show you our aim is, okay, just for you to understand, our aim is, if I can simplify, I need to simplify this part. If I can show it, it's equal to this one, k plus 4, instead of, and I'm just putting k plus 1, I'm just showing the aim where I'm going for k plus 2. If you can simplify and show it this one, then it means that if you simplify this part and show it equal to this one, it means you are correct. The statement is true. So let's do it. How we are going to do this one from our assumption equals to this y, right? So it will be k plus 3 divided by 4 k plus 1, k plus 2 plus, now the k plus 1 step, k plus 1, k plus 2, and k plus 3. I wish I have chosen the easy question with the little writing. So here we need to just equal the denominators. So as you can see, for the first fraction, I have to give k plus 3 and 4. For this one, k plus 3, and for this one, 4. Okay, now let me just deal with the numerator. Let me don't write denominator. So if I go with the numerator only, let me just simplify it. What will be numerator? K, it's a k plus 3, so it's k plus 3 square. K plus 3 square plus 4. Now from here, if you open the brackets, it will be k cube plus, because k square will be 6k square plus 9k plus 4. If you do factorize it from the polynomials, if you remember, it will be k plus 1, k plus 1, and it will be k plus 4. If you do not believe, you can open it, so it will be the same expression, plus k plus k. So from here, as you can see, in numerator for this expression, let me write here, we will have in simplified form k plus 1, k plus 1, okay, I could write k plus 1 squared, k plus 4 divided by 4 times k plus 1, k plus 2, and k plus 3. And from here, this one will cancel, one of the k plus 1 will cancel, and what we will have this expression, our aim. So here, since the first step is true and also the k plus 1 step is true, whenever the k step is true, we say that this statement is true for all positive integers.